Good morning, mechanical engineers. Welcome back. So today I'm going to just do some brief notes on bolts and bolt specifications. Again, the actual PowerPoint lecture is posted on D2L, and hopefully you've had a chance to go and have a look at that and before you look at this video. So again, this video is intended just to support that lecture, and so rather than me just reading through the lecture, I posted that, you read that, and then this is just some supporting notes. Excuse me, got some problems with the light here. Some supporting notes on that lecture. So today we're just going to look at the specification for bolts. We're not, the follow-on lecture will get into the analysis and details of the stress analysis a little bit more. So today we're just going to talk about how you basically specify bolts and why we use bolts. So bolts are a form of non-permanent fastening, and there are various other types of non-permanent fastenings that you can come across. Velcro, clips, locking tabs, there's a whole bunch of other stuff, but bolts are by far the most popular and universal. And these are great because they allow remote, or we call field assembly of parts. And you can do that, remote from the place of manufacture if it's a big assembly. Also, obviously, you can then disassemble it as well. Sure I spelled that one right. Disassemble. You can take things apart for maintenance to get access to sensitive parts, and also bolts allow adjustment. So by loosening bolts, moving parts around, you can adjust, and so again, very useful for stuff that we have to take apart, clean filters, replace worn out parts. We can open it up and maintain it and adjust it. So tremendously important. Bolts weren't originally standardized. Everybody was making their own, but obviously that becomes a problem when you want to mix up different assemblies. And it's still an issue to the sense that if you're not careful, English threads and metric threads are different, and they can look similar. And I worked for a company called Lucas Aerospace, which made the starter motors for aircraft engines, and we were a metric company, so all the stuff that we made was metric, but it was going on an American aircraft, so we had to make the external casings with American standard threads, which was great as long as nobody ever took one part, the inside apart, and had those bolts mixed up with the external parts. Then you'd have a complete mess. So we are better than we used to be, but we're still not universally standardized. So we do have standards, and the American one that we're interested in is called the American National Thread. Or the Unified Series. And that has the symbols UN, just UN for the normal use threads. And within the UN standard we have so-called UNC, which is for coarse, unified coarse threads, and we have unified fine threads, and then one that you've probably not seen much of is UNEF, unified extreme fine, or extra fine. So this is for your kind of run-of-the-mill application, regular stuff. This is for where we have vibration as an issue and the bolts can actually shake loose. So we'll use fine threads, so automotive and rotating machinery, that kind of thing. And if it gets really significant vibration, like for aircraft, and it becomes important, then we'd use the extra fine. Aircraft and instrumentation. There is another subset of UN called UNR, which has the root radius of the thread. We'll talk more about that in a minute. Is bigger, and this is to improve fatigue. So again, unified is the American standard, the UN, followed by a C or an F or an EF, depending on the thread type. And then if it has an R, then the root radius of that thread, and this is the coarse, is larger, so as you actually improve the fatigue life. So UN, UNR, well, there'll be UNC, UNF, UNEF. These are the ones that we normally look at. These are the most common ones, UNC and UF, and what we'll deal with in this course. With the metric standards, they have the subscript M for normal, which is our equivalent to UNC, and then for some strange reason they have the MJ, which is so you'll have metric, and that's your root radius increase, and then you've still got your metric, coarse and fine as well. So again, in this course we'll be more concerned with the American one, because that's the one we're going to be dealing with here in the US, but metric also has its equivalents. With regard to the thread, we'll look at the unified thread here. How do we create a unified thread? Well, basically it starts life, if you think of it, if we want to construct it as a equilateral triangle, sorry, not an equilateral triangle, it's a 60-degree triangle, which is actually an equilateral triangle. What am I on about? So this would be, if you think about it, this would be where we cut the thread, and then what we do from tip to hip tip here would be what we call the pitch. And to create our thread, we also have the height H here, and the pitch is from here to here. And just by trig, this is a 60-degree triangle, you can actually relate the pitch to the height, so that the height H, just from trig, is √3/2 times the pitch. So once you know the pitch that you're going to use for your bolt, which will be specified depending on the coarse or fine thread, then we've got the height and pitch relationship here. So we start with the 60 degrees, and then to actually create the thread, they effectively lop the top off, because that will just break off. So that distance that we lop off there is about 1/8 of the pitch. And then we go down to the bottom and we effectively lop off 2/8 down here. So that distance there becomes 2/8. So our thread effectively is like this truncated triangle. So this here is 2/8 of the pitch. This is 1/8, which means that this distance here makes up the difference of the 5/8. So that becomes your 5/8 of your height H is from there to there. So this is what your thread. It's how you construct it. So basically it's kind of a lopped off equilateral triangle, and the idea then is we don't break off the thin point when we interlock those threads. The other parameters that you need to know is this external distance here. We would call our pitch diameter. Sorry, that's our diameter, sorry, not our pitch diameter. Diameter of our thread. It's the external diameter, or the, yeah, we'll call that the external diameter. The pitch diameter comes in around here. Okay, so pitch diameter is effectively 2/4, 2/8 of that distance, and that there is 3/8 of the height, and that's 2/8, where that's the height h over here. So this is your 5/8. So 2/5 of the distance of the actual tooth height is what we call the pitch diameter. And then this last diameter down here is the root diameter. Okay, so there's kind of a lot of information there, but just background information. So you have your pitch specified for the type of thread that you want. From that pitch, you can calculate the height. √3/2 times that gives you the height. That equilateral triangle, we effectively lop off the top 1/8 and the bottom 2/8 or 1/4 to make our thread. That thread, that 5/8 of that height h there, is broken down to 3/8 and 2/8, and that line through the middle is what we call our pitch diameter, dp here. And the root diameter is the smallest diameter where the thread, or the tap, the die cuts in, and then the external here is the external diameter d. So that's kind of a bit of a background on how you construct those threads. Obviously, if you're cutting those threads with a lathe, you'll set the cutter up to make this. You'll have the cut bit to make this profile, and then you'll set the pitch. And if you are actually cutting it with a tap and die, then you make sure you use the correct tap and die to give you the appropriate thread. Okay. So a little bit on bolt materials now. So going back to our good old stress strain graph. So as you increase the stress, the strain goes up kind of linearly, and then it goes a little bit off linear, and then it eventually goes up until it breaks. So there's 3 points on this graph that we're interested in. There's the ultimate, there's what we call the yield, and then there's the proof. So this is the proof strength. So let me label the axis here: stress, strain. So that's the proof strength. That's the yield strength. And this is the ultimate. So the proof strength is basically, this is the end of the straight line part of our stress strain curve. There is a little bit here where it goes non-linear to the yield point, but if we were to remove the stress at this point, it would still go back with no deformation. Once you go past the yield point though, you come back, there'd be some deformation left over, some residual deformation. For the purposes of what we're interested in, this is what we will typically use for static strength of bolts. So it's a little bit less than the yield strength. Okay, so when we specify that, we go to table 8.9 in your Shigley textbook. There is some SAE specifications for the bolt, and the way this is done is the top of the bolt, if I've got one here, show you. So the top of the bolt, I'm not sure if you can see it, has some marks on it, and this one has 3, and that gives you an idea of what the type of bolt is. If there's no marks on the bolt, so looking at, again, this is for a kind of standard hex bolts, then this is really, we assume it's a grade 1. We call it SAE grade 1. If there is 3 marks on the bolt, which this one just had, then that's a grade 5. And then sugar. If there are 6 marks, then that's a SAE grade 8. And just for example, if we consider just the grade 5 here, it tells you in table 8.9 that for 1/4 inch to 1 inch, grade 5 has a proof strength of 85 kpsi, and once it gets above 1 inch, so it goes from 1 and an 8 is the next size up after 1 inch to 1.5 inch, that proof stress actually drops to 74 kpsi. So the bigger bolt's actually not quite as strong as the smaller bolt. So that would be for a grade 5. And table 8.9 gives you that information for those different grades of bolts. Table 8.10, and there's copies of this I think in the lecture notes. Table 8.10 gives you the American Society of Testing Materials bolt specifications, and then table 8.11 gives you the metric equivalent to those 2 tables. Another useful table you'll find in Shigley is table 8.2. Again, so table 8.2 is another kind of important one that you want to look at, and that gives you diameters and areas for UNC and UNF bolts. And it gives you one particular useful area is called the tensile stress area, which is the equivalent unthreaded rod diameter for the same strength. So typically that's the pitch diameter plus the root diameter over 2, which is kind of basically if we took a rod with no thread on it of that diameter, this diameter here, the equivalent diameter would be of the same strength as our actually threaded rod, and obviously that's going to be a smaller diameter because as soon as you thread it, you've effectively reduced the area, but you haven't actually quite reduced it to the root. Some people will use the root area when they're doing stress calcs just to be a little bit conservative, but it does act a little bit stronger than that. Okay, so some more details on bolts. If we look at the actual shape of a bolt, obviously from the side view here, we've got the bolt, and then there's a thread on this bolt, and then there's the hex head here. Some dimensions of interest, obviously there's the nominal diameter, D. So it's a 1/2 inch bolt. That diameter will actually be slightly less because it's got to go into a 1/2 inch hole. So there'll be the nominal diameter, there'll be a length of the bolt usually from the end of the bolt to the face, or if there's kind of a washer insert on the face, it'll be that distance there. And then there's the threaded length here of the bolt, and then there's the head of the bolt has a width on the face. So we can look at this from the front. There's we call it across the flats, that width there, W, looking at it from the end. Actually, that's first angle projection, but you get the idea. This width W is usually, it's approximately 1.5 times the diameter. And then for the American Unified series, the threaded length typically is 2 times the diameter plus 1/4 inch. That's for bolts where the length is, overall length is less than 6 inches. If it's more than 6 inches, it's 2 times the diameter plus 1/2 inch for greater than 6 inch length bolts. So for example, the bolt I have here, this is a 4-inch bolt, and if you apply that, the diameter of this bolt is 3/8 of an inch. So 2 times 3/8 gives me 6/8 plus 1/4, so that's another 2/8. Effectively, it gives me basically 1 inch. So the threaded length of this bolt here, I'll take the nut off, you can see this length here is of the order of 1 inch. And that's a 3/8 bolt. And then if you measure the distance across the flats here, that would be 3/8 times 3/2, 1.5, gives me 9/16, which is what that is, about 0.55. So that's 9/16. So that's a American standard UNC bolt. It's got threads on here. I've got a thread counter. This tool here lets me measure the threads, and that gives me 16. So 16 threads per inch is the actual specification, and that's correct for this one. That's a UNC bolt. And so you can get an idea of the threads on that one. It's coarse. And to just show the difference, I've got 2 other bolts here. I've got one that is another UNC coarse bolt. Sure you can see that. That's coarse thread. And then next to this one, similar bolt but with a fine thread. So same diameter bolt, and you can just physically see the difference in the threads there. So the fine one here would actually be much better for vibration, much less likely to come loose than this. If you think of the threads as a slope, falling down the slope, it's a steeper slope on the coarse threads than it is on the fine threads. It's much more shallow thread. So the bolt's much less likely to come undone. And so there's, again, you have to be careful. It's trying to thread the coarse one into the fine one. You can cross thread it and damage it. This is a fine nut, so you've got to make sure you have the right, be the right diameter, but you have the right thread to fit the right bolt. And there's standards, again, given in your book for the UNC and UNF. So for a given diameter of bolt, you can work out how many threads per inch you should be using for the standard in your table 8.9, 8.10, 8.2. They'll give you the standards for the threads per inch. Okay, so with that done, one more thing to look at in this lecture is how do you designate a bolt. So designation. So the way we designate bolts is we typically start with the nominal size. This is not the actual size, it's the nominal size. The threads per inch, TPI. Product length, so screw or bolt. Not nuts. And the product name, if it has one. The material. And any special finish, if it's plated or whatever. So stuff at the end here doesn't always appear. Critical stuff is the first few. So some examples. Let's do, so this would be a 3/8 bolt. Then you put a dash, 16 threads per inch, which is just like the one we just saw. So 3/8 nominal diameter, 16 threads per inch. We want a bolt, say 1.5 inches long. That one was 4 inches, but so we want 1.5 inch. maybe a square end instead of the hexagon. So a square bolt, we'll call it, square end bolt, made of steel, and maybe one a special finish, maybe a zinc plated finish on it. So that's an example. Another example, maybe a 1/2 inch bolt, 13 threads per inch is the standard. So if you've got the 1/2 inch, you know it's UNC. You could just put UNC, and then people figure out 13. We can call that the hex cap head, hex cap screw perhaps, so it's not actually a bolt. Hex cap screw, SAE, so it's SAE grade 8, and then we can also put in steel there. One more, 3/4 inch, 16 threads per inch, called a heavy hex nut, and then we'll give that an SAE J995 is the product name, and material is a grade 5 steel. So again, it's giving you some, oh, I didn't put a length in here, 3/16, let's call that, neither of those did I put a length, times 3 inch times 4 inch. Okay, so yeah, I missed the important dimension here, apologies. So diameter, threads per inch, length, description of the head of the nut or bolt or screw or bolt, and then the material description. Let's do one more, 1/2 inch, 13 threads per inch, 4 inch hex, SAE grade 3. That's probably what you'll see on drawings a little bit more, so it's a little bit more brief. And sometimes they'll actually even put in here with the threads, they'll actually put UNC or UNF just to reinforce that this information is a little bit redundant, but they will sometimes put the UNC or UNF in there as well as the threads per inch. It's like belt and braces. Okay, so quite a lot there today, and that's just the background on bolts and threads. There are a whole bunch of other standards. One of the ones I've been using is the pipe thread dimensions. The pipe threads are actually kind of interesting because the thread actually on the end of the bolt, if you will, exaggerated it here, is tapered. And the idea then is that as the nut comes on, the diameter increases, so you actually lock it into place and seal. So this would be your pipe thread. So that's a really useful one that I've found as well. The specifications for the threads actually tend to be the same for the nominal diameters, so it'll be 13 threads per inch, 16 threads per inch, wherever it'll still be there, but there is a taper to these standard pipe fittings. So that's another very useful one between the pipe and the UNC and UNF. That covers most of the applications we'll come across, and we won't use the pipe too much, but it's good to be aware of that one. Okay, so that's it for now. The next lecture we'll get into the details on pre-stressing bolts, so bolts that are in tension, and then after that we'll have another series of lectures on bolts that are in shear. So there's two subjects. This is just a background on picking a bolt. Once you've done the analysis, we've kind of done that up front. We're going to do the calcs now to determine which of these bolts we're actually going to use. But obviously bolts, you can clamp material together with a nut on the end here, and that would be a bolt in tension when it's actually clamped. And we actually pre-stress them by squeezing the bolt down, tightening the nut up. We stretch the bolt and we pre-tension it. So that's a pre-tension is very important. We'll talk about that more. That's bolts in tension. So that's going to be the subject of the next one. And then apart from that, we obviously have a situation where we can have a bolt and we can have a plate like this and a plate like this, and by pulling down on this one and pulling up on this one, we've effectively put a nut on here to secure the thing in place. This bolt here is in shear here. Here it's in tension. but here the bolt is in shear, and there it's in tension. So these are the two topics of the upcoming lectures. This one was just to give you a background on the specifications. All right, so with that, I'll stop there for now. Hopefully that's helped, and talk to you on the next one.